Hello students, so we'll just continue our class from the previous video. In the previous video we've discussed about the different types of bond fission or bond cleavage, and we have also discussed inductive effect, and we have discussed resonance. Okay, so in this video we'll start with Mesmeric effect. So Mesmeric effect is a effect which follows resonance. Okay, means resonance is a phenomena which is used in which is used to explain Mesmeric effect. Okay, so it is same. Mesmeric effect is also a delocalization of pi electron, means electron displacement effect. Okay, in inductive effect what we had sigma electrons that are used. Okay, means only the sigma electrons are participating in movement, but in Mesmeric effect what happens, the pi electrons will participate in movement. Okay, this is exactly the same thing that I've explained in my previous video. If you have not watched it, just go and watch it once. In the previous video I have discussed about resonance, means if you have electron donating groups or electron withdrawing groups, what are the different types of resonance that are possible. Okay, so in Mesmeric effect same thing happens. Okay, so Mesmeric effect is of two types. One is plus m, another one is minus m. Okay, and plus m effect is possible when electron donating groups are there, and minus m effect is possible when electron withdrawing groups are there. Okay, so that you see plus m you can also correlate with plus r, means positive resonance, and minus m you can correlate with minus r, like negative resonance. Okay, so same thing, if you have electron donating groups, it will donate electrons to the ring. Okay, means arrows will be moving towards the ring. Okay, and if you have electron withdrawing groups, it will take electrons, means pull electrons from the ring. Okay, so arrows will be going toward away from the ring. Okay, so the first point that you have to keep in mind is that Mesmeric effect, it it is only applicable in conjugated systems. Okay, means pi electron system or conjugated systems. Okay, it depends upon electron donating group or withdrawing group. If you have electron donating group, then you will get a positive Mesmeric effect, means arrows, means movement of electrons or delocalization of electrons will be from the group, means from the electron donating group towards the ring. Okay, and if you have electron withdrawing groups, then you have movement of electrons or delocalization of pi electrons from the ring towards the electron donating group, electron withdrawing group. Okay, then third point is that it is a push or pull mechanism. Okay, if you have electron donating group, it will be push. If you have electron withdrawing group, it will be pull. Okay, and last one, it is a permanent effect, means inductive effect is also a permanent effect. Mesmeric effect is also a permanent effect, because the group will be permanently, means the electron withdrawing or donating group will be permanently present in the compound. Okay, so that's why these two effects are permanent effects. Okay, so next we'll be discussing Electromeric effect. Okay, now say Electromeric, previously we discussed inductive effect and Mesmeric effect. Those are permanent effects, and Electromeric effect, it is a temporary effect. Okay, Electromeric effect means what you see, say if you have a pi system, say you have ethene. Okay, now this pi system, you see this carbon carbon double bond, this pi electrons can break, either it can go in this carbon. Okay, if it goes in this carbon, this will have a minus charge, this will have a plus charge. Okay, and it can be opposite also. Say the pi electrons can go to the first carbon, if it goes to the first carbon, it will have a minus charge, it will have a plus charge, means both ways are possible. Okay, both possibilities are there, and both are having equal probability. Okay, but now see, the catch comes here only. Say if you bring a electrophile, means electron deficient species, nearby to that alkene. Okay, now see, if the electrophile is near to this second carbon, okay, say just number it 1 2 1 2, if electrophile is near to the second carbon, okay, then electrons will be moving towards the second carbon. Okay, because electrophiles are electron deficient species. Okay, and this pi bond is a, means electron rich species. Okay, so pi bond will give electrons to this second carbon, because it is closer to the electrophile, and it is because a minus charge means opposite charges will be formed now, so that will be stable. Okay, means just like in physics you have studied now, say if you have a neutral system where plus charge and minus charges are equally distributed. Okay, so in that system if you bring say a positive charge nearby to this system, okay, then what will happen, you see, this will be like this. If you bring positive charge nearby to the system, polarization will be taking place, and the negative charges will go in one side and the positive charges will be going in one side. Means previously this system was uniformly distributed, okay, with positive and negative charge, and when a positive charge is brought nearby to this system, what happened, polarization occurred and minus charges came in one side and plus charges went in the other side. Okay, so same thing happens in this alkenes also. Okay, so similarly this effect, say if you bring an electrophile near to the second carbon, then it will be electrons will be moving towards the second carbon. Okay, now if you bring a nucleophile, okay, if you bring a nucleophile near to the second carbon, then electrons will be moving towards the first carbon, means it will go away from the second carbon. Why? Because nucleophile is a electron rich species, okay, and it has excess of electrons. So if it is near to the second carbon, then the pi electrons will be going away from the second carbon, because we know that like charges repels and unlike charges attracts. Okay, same thing happens here. So you just see, if electrophile is used, then this pi electrons will be coming nearer, will be shifting towards that carbon which is nearer to the electrophile. Okay, and as a result we will get a carbocation intermediate. Okay, and if say you have nucleophile, okay, the nucleophile is totally opposite. Nucleophile will attack the carbon which is nearer to the nucleophile, and the other carbon will get the electrons and it will give a carboanion. Okay, so these are the two types of electromeric effect that is possible. If you use a electrophile, it is called positive electromeric effect, because we get a carbocation, means positive charge, and if it is a nucleophile, we will get a carboanion, so it is a negative electromeric effect or minus E effect. Okay, so this electromeric effect is a temporary effect, because it is only possible if you give electrophiles or nucleophiles. Means if you give external agent, then only this effect is possible. Okay, and as soon as you remove the electrophile and the nucleophile, you will get the alkene back. Okay, so that's why this effect is a temporary effect. Next, let us move on to hyperconjugation. Okay, so hyperconjugation is a very important topic. It is similar to resonance only. Okay, resonance, what happened, delocalization of pi electrons take place. In hyperconjugation, what happens, sigma electrons will be delocalized. Okay, and in resonance we move, the electrons move in a bonded structure, means a bonded network is there. But in hyperconjugation, what happens, no bond is present. Okay, means the atoms will be floating around. Okay, and no bond will be there. That's why it is also called as no bond resonance. Okay, so first condition for hyperconjugation is that you should have at least one sp2 hybridized carbon. Okay, means sp2 hybridized carbon you should have. Means for example, you should have alkene or carbocation or free radical, because carbocations are sp2 hybridized, free radicals are also sp2 hybridized, and alkenes, means carbon carbon double bonded compounds, are sp2 hybridized. Okay, so you should have at least one sp2 hybridized carbon in the system. Okay, second point is that alpha hydrogen should be present. Okay, alpha hydrogen means, you see, the, say anything, say you have a carbocation carbon, next carbon, then carbon. Okay, so like that. So the carbocation carbon is connected to this carbon, the second carbon. Okay, this one. So this second carbon, now this carbon is called your alpha carbon. Okay, the second carbon means the adjacent carbon to the carbocation carbon, means the adjacent carbon to the sp2 hybridized. This carbocation carbon is sp2 hybridized now. So the adjacent carbon to the sp2 hybridized carbon is your alpha carbon, and the number of hydrogens that are connected to this carbon are called your alpha hydrogens. Okay, so if alpha hydrogens are present, then only hyperconjugation will be possible. Okay, so two conditions for hyperconjugation are that first one, you should have sp2 hybridized carbon. Secondly, you should have a alpha hydrogen. Okay, means the carbon next to the sp2 hybridized carbon is your alpha carbon, and number of hydrogens attached to that alpha carbon is your alpha hydrogen. Okay, so let us check the examples. You see this one, this molecule, it is having a this one carbon carbon double bond. Okay, so this two carbons now, this one double bonded carbons, these are your sp2 hybridized carbons. Okay, so sp2 hybridized carbon, you see on this right side you don't have any other carbon, so alpha carbon is not there, but in the left hand side you have this carbon that is attached to the sp2 hybridized carbon, so this is your alpha carbon. Okay, so this alpha carbon has three hydrogens, so these hydrogens are called your alpha hydrogens. So in this structure you have three alpha hydrogens. Okay, and one thing if you keep in mind that alpha hydrogens will be equal to number of hyperconjugating structures. Means if you have 5 alpha hydrogens, then total number of hyperconjugating structures will be 5. Okay, and same thing just as you did in resonance now, the number of resonating structures decides stability. Means more number of resonating structures means more stable. Similarly, if you have more number of hyperconjugating structures, then it will be more stable, and we know that more stable, then it is more acidic. Okay, so you can relate stability and acidity also with these things. So along with this you can means these are the applications of these different types of effects. Okay, to find out stability, to find out acidity, basicity, like that. Okay, so you see first one, what will happen, this pi electron will be transferred to the other carbon, means the terminal carbon, and you will have a plus charge in this carbon, the central carbon. Okay, and to balance the plus charge, this carbon hydrogen, this sigma electrons now it will donate. Means carbon hydrogen one sigma bond is there, no? That bond will donate electrons to balance the plus charge on the central carbon. Okay, so you will get this structure and with a H plus ion floating around. Okay, so this structure is called your hyperconjugating structure. Okay, now see you have three alpha hydrogens. Okay, so in every structure one alpha hydrogen will donate its electrons, so you will get three structures. Okay, so these are the three hyperconjugating structures that are possible for this compound. Okay, now this is for hydrogen. If you have alpha hydrogens, then these structures are possible. Okay, now in place of hydrogen, see hydrogen is a electropositive element. Okay, if you have a electronegative element, say for example halogens, then the process will be reverse, and it is called reverse hydrogen hyperconjugation. Means the movement of arrow will be reverse. So this time the arrows will be moving towards the electronegative atom, and you will be getting Cl minus ions. Okay, so this also same, it depends upon the number of alpha atoms. Okay, so this is called reverse hyperconjugation. Clear? So this topic is not that tough, it is easy, only just to know that how you draw hyperconjugating structures. And in exam you don't have to draw hyperconjugating structures also, you just find out the number of alpha hydrogens. Okay, if you count the number of alpha hydrogens, then you can easily write that how many hyperconjugating structures you have. So if you have 3-4 structures given to you and they will ask you to arrange them in order of stability, you just count the number of alpha hydrogens, and whichever has more number of alpha hydrogen will be more stable. Simple. Okay, so let us come to the applications of electron displacement effects. Okay, so first application is you have to means we can find out the stability of intermediates. Intermediate means carbocations, carboanions, and free radicals. Okay, so carbocations and free radicals, since both are stabilized by electron donating groups, so their properties will be same. And carboanions are stabilized by electron withdrawing groups. Okay, and we know that electron donating group means plus I effect. Okay, so if you have electron donating groups, or if you have plus I effect, then carbocations will be stabilized. Okay, similarly if you have electron withdrawing groups or minus I effect, then carboanions will be stabilized. Okay, and this opposite is also true. If you have electron withdrawing groups, then it will destabilize carbocation or free radicals. Similarly, minus I effect will destabilize carbocations and free radicals. If you have electron donating groups, then it will destabilize carboanions. Okay, so here are two examples. Say you have this one, you have CH3 groups. Okay, I'm just explaining this on only for electron donating groups. Okay, electron withdrawing groups, you write it yourself. It is just exactly opposite of what electron donating groups have. Okay, so electron donating groups, you see in this carbocation we have 3 electron donating groups. Okay, in the next one we have 2, and in the third one we have 1, and the fourth one does not have any electron donating group. Okay, now I told you that carbocations are electron deficient species. Okay, so if you have a electron donating group, then it will stabilize a carbocation. Just this one, you see, first formula, electron donating group stabilizes carbocations and free radicals. Okay, so the order of stability will be, this has 3 carbocations, so it is high stable, then 2, then 1, and then no electron donating groups. Okay, similarly carboanions, it is destabilized by electron donating groups. Okay, say if you have electron donating groups, it will destabilize the carboanion. So you see here you have 3 electron donating groups. So you see this carboanion carbon, it is having a minus charge, means the carbon already has excess of electrons. If you give more electrons to the carbon, then it will be more unstable now. So 3 electrons will be the most unstable, then 3 electron donating groups more unstable, then here you have 2 electron donating groups, and here you have 1, and here no electron donating groups. So this is the most stable out of all these 4. Okay, so electron withdrawing will be opposite. Electron withdrawing, just you write the order. Okay, so do it by yourself for electron withdrawing groups. Okay, and this is your homework. So in this way you can find out the stability of carbocations, anions, and free radicals. Okay, free radicals will be exactly same as carbocations. Okay, okay, it's gone. So let us come back to the next application. Next application is strength of an acid. Okay, so using this carbocations and anion, this different types of effects, we can easily find out the acidity. Okay, acidity, I told you only that if you can find out stability, then acidity will automatically you can easily find out. Okay, because stability and acidity is directly proportional. Okay, now acid means one which gives H plus ions. Okay, say this is acid Ha. Okay, if it gives H plus ion, then only we can call it a acid. Okay, now see this acid Ha, it gives H plus ions. After giving, we get A minus ions also. Okay, now this A minus ion can again take this H plus ion, because this is negative, this is positive, this can take this H plus ion, and we can get this acid back. Okay, so acid means which donates H plus ion. Okay, and base means which accepts H plus ion. Clear? Now if we say that Ha is a acid because it gives this one, because it gives H plus ions, we can also say na A minus is a base as it takes H plus ions, because this reaction is in equilibrium. Okay, means it's reversible reaction, both sides are possible. So you see this thing, this base na means A minus is acting as a base, so we'll call this base as a conjugate base. Okay, we'll call this base as a conjugate base. Conjugate base means this is not actually a base, but it is formed from an acid, means acid after giving H plus ions, it becomes a base. Okay, so it is called a conjugate base. Now first and most important thing that you have to know is that this acid will give up H plus ion only if this conjugate base is stable. Okay, because after giving H plus ion, this is also the acid is left with this structure na A minus. So if A minus is not stable, then why it will give H plus ion? Okay, so always keep in mind that acid is means acid will be more acidic only if the conjugate base is more stable. Okay, because if the conjugate base is stable, then only it can easily give up H plus ion. But if the base is not stable, means after giving H plus ion, the resulting compound, if it is not stable, then why it will give the H plus ion? Okay, so you just try to understand the point. So you see, so we can say that strength of an acid it is directly proportional to the stability of the conjugate base. Okay, the more stable the conjugate base is, the acid can more easily can donate the H plus ion. Okay, so if it donates H plus ion more easily, then the acid is more acidic. Okay, so we can say that strength of an acid, it depends directly on the stability of the conjugate base. Okay, so you just memorize this formula. Say acidic strength, it depends upon electron withdrawing groups or minus I effect. Okay, because let us take this example. Say you have this one. Say let us just take the easy one. CH3 COOH. This is acetic acid. Okay, now this acetic acid will release, say we will add one more group to this CH3. Say let us make it CH2, and another group is here. Say it is X. Okay, now this group X, if it is a electron donating group, okay, if X is a electron donating group, say you have X as a electron donating group. Okay, if X is a electron donating group, it will donate electrons to CH2. Okay, CH2 will donate electrons this carbon, and this carbon will donate electrons to this oxygens. Okay, so this oxygen is getting electrons from this left hand side. Oxygen is electronegative. Okay, it is already getting electron density from this left hand side. So why it will take electrons from this hydrogen? It will not take. Okay, because it is already getting electrons from this CH2 groups, this X group. Okay, from all the groups that are present in the left hand side, is already getting electrons, so it has no use of taking electrons from this hydrogen. Okay, so if it does not take electron from this hydrogen, means this bond it will not break. If this bond does not break, then this H group will not go out and the acidity will decrease. Means if you have electron donating group, then acidity decreases. Okay, then acidity decreases. Clear? Now let us, same thing, let us take X as a electron withdrawing group. Okay, say X is a electron withdrawing group. Okay, so if X is a electron withdrawing group, so it will be exactly opposite. So it will be like this: CH2 double bond OH, like this. Okay, so X is a electron withdrawing group, so it will take electrons from this CH2 group. CH2 will pull electrons from this this one carbon. Now see, this carbon is attached to a double bonded oxygen and a single bonded oxygen. Okay, so double bonded oxygen is more strong, so it will pull electrons from this carbon, it will not give. Okay, so single bonded oxygen will not get any electron from this left hand side. Okay, single bonded oxygen will not get any electrons from this left hand side because this carbon is already electron deficient. Okay, so what will happen, it will take electrons from this hydrogen, and as it will take electrons from this hydrogen, this bond will break. If this bond will break, this hydrogen can go out easily, so acidity increases. So acidity increases. Okay, so this is the basic concept that is used here. If you have electron donating groups attached to acid, it is its acidity decreases, and if you have electron withdrawing group attached to acid, then its acidity increases. Okay, so let us come to the next one. It is strength of a base. So strength of a base, how you will find out? You see, basicity or strength of a base, it is defined as the availability of lone pair present on more electronegative atom. Okay, so if you have nitrogen, then it will be availability of lone pair on nitrogen. If you have oxygen, then it will be availability of lone pair on oxygen. Okay, so basicity, how you will find out, means strength of a base, how you will find out? You see, two things you have to keep in mind. Okay, first thing, availability of lone pair on, means availability of electron pair on more electronegative atom or nitrogen atom, And second thing is that it should be able to donate the electrons also. Okay, means nitrogen, if it is having lone pairs, it should be able to donate this lone pairs also. Okay, so we can say that if you have only hydrogens surrounding nitrogen, okay, then nitrogen is more electronegative than hydrogen, so it will uh, pull electron density from this hydrogens, and this lone pair will be completely available on nitrogen, so it is basic. Okay, this is more basic. If you have a aromatic ring, say you have aniline, this question also I think you have studied in your class 12, why ammonia is more basic than aniline. Because you see in aniline what happens now, this pi electrons will go into resonance, means it is not available in nitrogen, so it is less basic, so basicity of ammonia is higher than aniline. Okay, this is one fact. Secondly, what you can have, you see, you have this nitrogen, means it is amine. Okay, and you have bulky groups here, means you have CH3, you have CH3, you have CH3. Okay, so if you have bulky groups, then this lone pair will not be available in nitrogen. Okay, this lone pair will not be, means lone pair will be available because these are electron donating groups. Lone pair will be obviously available in nitrogen, but this lone pair will not be available for donation. Okay, why it will not be available for donation? Let me draw another structure. Why it is not available for donation, you just see, say this is nitrogen, this nitrogen is having three bulky groups, means say CH3, CH3. Bulky groups means, you know, it's large groups. Okay, so like this. Okay, and it has a lone pair in it. Okay, so since these groups are bulky means these groups are like this. Okay, if you just spread the hydrogens, it will be like this. Three hydrogens will be placed like this. Hydrogen, 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 here also hydrogen, hydrogen, hydrogen. Okay, so since all the hydrogens are spread, so it is very bulky, so this lone pair, it cannot go and reach other atoms, means it cannot donate, this nitrogen cannot donate its lone pairs. Okay, because it is already crowded. Okay, so there is no space for this lone pairs to go out and reach other atoms. Okay, so that's why basicity decreases. So first point is you should see availability of lone pair. Second point is more important, says that the steric hindrance should be 0, means the lone pair should be available for donation. So that aniline and ammonia example, though it is easy only because ammonia has aniline has this one has resonance, so pi electrons will not be available in nitrogen, whereas in ammonia pi electrons will be available in nitrogen, so ammonia is more basic than aniline. Okay, but in this case, say you have ammonia and you have this one, say you have ammonia and you have this structure. Okay, CH3 CH3 CH3n. Okay, so in this case also ammonia will be more basic. You see, CH3 is a electron donating group. Okay, electron donating group, you all know that electron donating groups are it increases the electron density on nitrogen. Okay, because it will donate electrons to nitrogen, so no doubt electron density will be higher in nitrogen, means lone pairs will be more available in nitrogen. But the second point is not valid in this case, because this nitrogen cannot give its lone pairs. So if it cannot donate lone pairs, then it is not basic. Okay, so that's why this ammonia is more basic compared to this 3-degree amine. Clear? So the last topic for this GOC is attacking reagents. Okay, so attacking reagents are of two types. First one is nucleophile, second one is electrophile. Okay, so electrophiles are electron deficient species, all of you know. It is also called Lewis acids because it accepts electrons, and nucleophiles are electron rich species. It is also called as Lewis bases because it donates electrons. Okay, so one important thing is that nucleophile and base, okay, you will always make a mistake if you don't know this. I think that many students, if you don't know this, about 90% of students will not be knowing this concept, what is the difference between a nucleophile and a base, because this is very very important. Okay, so nucleophile and base, it is, you see, nucleophile also has a minus charge or lone pair, base also has a minus charge or a lone pair. Okay, but only difference in a nucleophile and a base is that is their way they attack. Okay, means the way they react. So you just see this example. You see, we have a system where you have a carbonyl group. Okay, now this carbonyl compound, this oxygen is more electronegative, so it will have a delta plus charge, delta minus charge. And this carbon, since this oxygen is pulling electron density from this carbon, okay, this carbon means this one. Okay, here you have a carbon now. This carbon, it is having this one less electron density, so it will have a plus charge. Okay, now you have a CH3 group here, and say you have a hydrogen here. Okay, this is a acetaldehyde. Okay, so what will happen, say this example I have taken. So if you have a base, say you have a base, then what base will do, I told you that alpha carbons are more acidic, means alpha hydrogens are more acidic. Okay, so this is alpha position. Alpha means the carbon that is next to the carbonyl group. This is your carbonyl group and this is the next carbon, so this is alpha. So these hydrogens are acidic. Okay, these hydrogens are acidic, so you have 3 hydrogens here. Okay, so this base, what it will do, it will take one of these acidic hydrogens. It will take one of these acidic hydrogens and it will give its electrons to this carbon, so you will get this product. Okay, means the product will be like this. You will get CH2 with a minus charge. Okay, so this will be the product. Okay, but if a nucleophile is present, okay, if a nucleophile is present, same thing, you see, same reactant I will take. Say you have this one, CH3 double bond O, here will be H. Okay, and you are reacting with a nucleophile. Okay, so if a nucleophile is present, what will happen, it will go and attack this electron deficient carbon, the carbonyl carbon, and this oxygen will open up. Okay, and your product will be like this. Nucleophile will be adding up here, you will have CH3 and you will have single bonded oxygen with a minus charge. Okay, so this is the difference between a nucleophile and a base. Base always abstracts acidic hydrogen, whereas nucleophiles attacks electron deficient center. Okay, so this concept is very very important. And you see GOC, you have so many small things, small topics. You just try to solve as many questions as you can from this GOC part. Okay, and I have also provided you with an assignment, so you just try to solve it and go through the materials that I have given you. So I think that will be enough for solving the questions in your exams. Okay, so with this this topic is over, means you see this chapter is over. In the next video we'll be discussing organic reaction mechanism, and I think it will be the last video for this organic chemistry part. And tomorrow I guess you guys will be getting your results, class 12 results. So all the best for your results and hope you do good in your results. So all the best guys, thank you.